In this class, we will learn about electric drives for electrical machines. This is the second video of the series, so check the last video to learn the previous topics. Before we continue, remember to subscribe in our channel, like the video and active the notifications, to help us grow in the platform. Chopper circuits and DC motor drives. A chopper circuit is an electronic circuit that changes a DC input voltage into a desired output voltage, which can be either higher or lower than the input. In DC motor control systems, the output voltage can be adjusted to vary the speed. Similar to rectifiers, these circuits can function across all four quadrants of operational drive, as required by specific circuit and motor operational demands. We will now explore the primary types of choppers, noting that switching is achieved using thyristors. The configuration shown in the diagram, consisting of capacitors, thyristors, diodes, and an inductor arranged in series or parallel, functions as a switch, S, that can be activated or deactivated. Through precise control, the average voltage supplied to the motor can be adjusted. The freewheeling diode, D2, permits the flow of current from the load to persist when switch S is open. This scenario is especially relevant when the motor behaves primarily as an inductive load. When the freewheeling diode conducts, it dissipates some of the energy stored in the inductor through the load resistance. Moreover, by selecting appropriate operating frequencies for the chopper and matching them with the load inductance, the output current can be regulated to minimize fluctuations. The relationships between voltage and current over time are typically depicted in accompanying figures. At this juncture, a crucial concept in electronic drives emerges: pulse width modulation, PWM. This technique enables the delivery of a variable signal to the motor, facilitating precise control over its operation. Similarly to thyristor rectifiers, it is feasible to configure the circuit so that the drive operates within a particular quadrant. The following examples illustrate chopper specifications, taking into account whether the motor necessitates operation in one quadrant, two quadrants, or all four quadrants. These circuits operate in a manner akin to the fundamental circuit discussed earlier. Assuming a DC source is consistently available, in the first scenario, a circuit is required to drive the motor to operate exclusively in the first quadrant. One potential circuit configuration for achieving this is depicted in the following figure. In the second scenario, where the motor needs to operate in the second quadrant, the drive circuit can be designed similarly to the previous one used for the first quadrant. However, in this case, the polarities of the diode and thyristor would be reversed. This adjustment allows for the flow of negative current and the supply of negative voltage to the motor during electronic drive. Consequently, the motor can operate in reverse and decelerate as needed. For acceleration and braking operations across all four quadrants, configurations similar to those depicted in the panel of the following figure are commonly employed. These circuits enable precise control over motor speed and direction by managing both positive and negative currents and voltages as required by the motor's operational needs in each quadrant. Finally, to drive a DC motor using a DC power supply and achieve variable operation across all four quadrants, chopper circuits can be utilized. One effective circuit configuration for this purpose is illustrated in the following figure. Electronic drives for AC motors with intermediate DC link. In the context of driving an AC motor, similar principles to those discussed earlier will apply. However, before delving into those details, it's essential to understand the concept of intermediate DC link drive. This approach to driving AC motors involves circuits that utilize either direct conversion topologies or, more commonly, an intermediate DC link. In this approach, AC voltage is initially rectified to generate DC voltage or current. This DC power is then converted back into AC voltage through an inversion process. This type of AC motor drive, within the broader system, is often referred to as a two-stage drive. Additionally, intermediate DC link topologies, also known as DC link, are classified into two main types: VSI, voltage source inverter, and CSI, current source inverter. These configurations play crucial roles in AC motor drives, offering distinct advantages depending on the specific application requirements. To initiate the operation of an AC motor, a circuit is required for AC-DC conversion, which can be achieved using a thyristor rectifier circuit, similar to those discussed earlier for DC motors. This rectifier circuit converts the AC supply voltage into a continuous DC signal, which subsequently serves as the input for the inverter circuit. The inverter, working in conjunction with the rectifier, enables precise electronic control of the AC motor. Inverters are pivotal in this setup as they convert the DC voltage into AC voltage through frequency inversion. Depending on the power supply configuration, inverters are broadly categorized into two main groups: VSI, voltage source inverter, and CSI, current source inverter. These categories determine the method by which the AC voltage is generated and controlled for driving the AC motor. Voltage source inverter, VSI. VSI circuits are further classified based on the modulation technique employed for DC/AC conversion. They can be categorized into PAM, pulse amplitude modulation, where the modulation is achieved by varying the pulse amplitude, or PWM, pulse width modulation, where the modulation is based on varying the pulse width. These modulation methods play crucial roles in controlling the output voltage and frequency of the AC signal generated by the inverter, thereby influencing the performance and efficiency of the AC motor drive system. Furthermore, it is important to mention that pulse ratio modulation, akin to chopper circuits, is utilized once more. To begin with, examine the circuit employing amplitude modulation. The entire electronic drive circuit, which incorporates a thyristor-based voltage source inverter, is depicted. This diagram represents a three-phase system, a standard configuration for most AC motors in numerous applications. For a system utilizing a current source inverter, CSI, the DC link voltage is alternately applied to the motor phases to control the inverter. Consequently, the inverter necessitates voltage control, which can be managed externally to ensure the motor operates efficiently. The drive circuit operates by varying the rectifier's control angle to adjust the voltage, allowing the inverter to run at a variable DC voltage and supply the needed frequency. When the inverter handles voltage control, it uses pulse modulation, as mentioned earlier. For a VSI, this can be achieved through pulse width or pulse amplitude modulation. The equipment regulates both voltage and frequency to drive the AC motor. However, there are some inherent disadvantages. For example, at low speeds, a current source inverter may not provide sufficient voltage for commutation, limiting its effectiveness for low-speed operation. Additionally, a voltage source inverter requires an extra converter for the AC motor to operate in regeneration mode. From a modulation perspective, VSI circuits are categorized as follows: VSI PAM for pulse amplitude modulation and VSI PWM for pulse width modulation. In a VSI PAM circuit, voltage control is achieved by adjusting the amplitude with a controlled rectifier at the input, while the inverter controls the frequency, making it a VSI with amplitude modulation. Conversely, in a VSI PWM circuit, a diode bridge is used in the rectification stage, resulting in an uncontrolled AC-DC conversion, with both the voltage amplitude and frequency controlled within the inverter. Current source inverter, CSI. When the DC link is established using direct current, we have a current source inverter, CSI. In a CSI circuit, as shown in the example, the DC link current alternates through the motor phases to control the inverter. This configuration simplifies the circuit setup by eliminating the need for feedback diodes. The following figure illustrates an electronic drive circuit for an AC motor using a rectifier and a thyristor-controlled inverter in a CSI, current source inverter, configuration. The rectifier modulates the current amplitude entering the inverter, while the inverter adjusts the frequency to achieve the desired motor operation. Additionally, the inserted inductor acts as the DC link, storing energy for coupling and decoupling processes. It enhances operational safety by mitigating the effects of power supply fluctuations, ensuring the motor operates correctly despite potential oscillations in the supply network. However, a current source inverter, CSI, is not ideal for systems involving multiple motors due to its inherent circuit design characteristics. Additionally, in practical applications, the DC link inductor often needs to have a high value to properly establish the intermediate loop. This requirement can significantly increase the cost, size, and complexity of the overall system. Moreover, as depicted in the circuit diagram, the use of multiple capacitors is essential to aid in the commutation of thyristors and thereby control frequency variation in this configuration. However, this necessity can also pose a notable disadvantage when employing this type of inverter. Keep with us in the next video to learn more about electronic drives, and let in the comments if you want to know something else. Bye!